what I was telling yesterday. I just want to maybe give quick or less quick responses to a couple of questions. One was yours about the correlation of the spectra in different samples and whether one can do it in one sample. So I already told that basically if you look at parts of spectra that are away from each other by tau less energy, they are not correlated. If you have nodes, you can see equation 16. And the correlations, according to the equation, basically it's R2 at function of omega, and omega, at omega larger than tau less energy, R2 is decaying. So the critical scale is tau less energy indeed. And this equation is okay for, because we assume that electrons are moving diffusively, it's okay to use it for omegas much less than 1 over tau, where tau is the electric mean free time. And that takes me to kind of a response to the question that we were at the very end of last hour. What are the relations between different methods of looking at statistics of levels and wave functions? And I can draw the following scheme. So if this is the scale for single level spacing, tau less energy, 1 over tau, and somewhere here, the f, maybe I should put arrow in opposite direction, 0. Then, I mean, simply here, there is no question. I mean, you cannot pose a question that I asked about statistics of levels. Random matrix theory, it's a phenomenological theory. It works for energies or different energy differences between 0 and much less than tau less energy. So RMT works here. Now, the perturbative in 1 over KFL methods that we actively used last hour, they work at for energy scales much larger than delta E, but much smaller than 1 over ET. So that would be here, and this is diffusion approximation. And it's a microscopic theory, meaning that I can take specific impurities with some scattering potential, calculate 1 over tau, calculate diffusion coefficient, and find everything I want in terms of the microscopic parameters of the system. There is overlap in the applicability of this and this. Okay? And this is a cheap way to read off parameters of RMT from microscopic calculation. Okay? It's a cheap way. A hard way is to do non-perturbative in 1 over KFL work, and that's basically the sigma model that Andrei was discussing. That basically gives a microscopic derivation of RMT for any energy scale. But even without that, due to this overlap, you can establish parameters of RMT, matching it to diffusion approximation. And finally, there's a slight extension of this thing. One can extend this further and go to the region which is even larger than 1 over tau. And that amounts to a very simple generalization coming from going from diffusive approximation to the kinetic equation. So basically, the meaning of diffusion is it's a solution of diffusion equation. So it's how the density spreads in a real space when you put a particle somewhere in the beginning, and more detailed information is about distribution function. So basically, if you introduce an object that knows how a particle with initial momentum p1 and coordinate r1 spreads in phase space, if you know this object, you can extend what we were discussing to the area short as 1 over tau. So this object is basically the solution of the kinetic equation also discussed by Andreev. I think he called it capital K or script K, something like that. And that all was done. So basically, extension of diffusion approximation to this region for the purpose of looking at statistics of levels was done some time ago by Atland and Geffen, perhaps early 90s. I didn't look for references. But Atland will be here, so you can, maybe he still remembers it. So you can ask him. Okay, so that's all about the remarks I wanted to make as the end of yesterday's our lecture. So now, basically, I want to discuss further the properties of RMT, and we discussed level statistics, but another important thing are the eigenvectors. So, as we discussed yesterday, basically, RMT is an ensemble of matrices M by M, where M is large. And again, mathematically, at the end, I should take M to infinity. Physically, M must be larger than the dimensionless conductance. So it's a matrix. It's a Hermitian matrix. It has real eigenvalues, and it has eigenvectors that are just columns of numbers, of M numbers, right? These numbers may be real or complex, depending on whether we're talking about unitary or orthogonal ensemble. So if it's a orthogonal ensemble, we can pick all the matrix elements real, and it's a consequence of time reversal symmetry, right? So if you have time reversal symmetry, you can always pick by functions real, therefore matrix elements will be real. And in the case of unitary ensemble, there is no time reversal, and matrix elements of matrix are complex, and respectively the eigenvectors are columns of real or complex numbers. From the form of the distribution function, which knows only about the trace of the matrix. So if you remember, we had in the definition basically yesterday this form, it's clear that the eigenvectors are random, and it's quite easy to show that they are independent of each other. So the distribution function, let's call it W, of the components of eigenvector alpha. Okay, so Ci alpha stands for a component I of eigenvector number alpha. I better use normalization, so I'll write it as a constant times delta of 1 minus sum over I from 1 to m Ci alpha squared. Okay, so the only condition on Ci is that the eigenvector is normalized, but the components of Ci's are otherwise independent. So, and as you see, there is no, it's only one alpha here. So there is no correlation between different eigenvectors. Ci alpha Cj beta is proportional to delta alpha beta. Now, one can ask a question. Yeah, so another thing that I should mention that statistically eigenvectors are also independent of energy levels. So Ci alpha epsilon beta is 0 even if alpha equals beta. Now one can ask, okay, so it's proportional to delta alpha beta. So if alpha equals beta, it's not 0. What is the distribution of C of Ci squared. So what is the distribution function of eta, where eta is m Ci squared. Let me put here so the way to do. Mathematically, it's a simple question, and I'm pretty sure that in calculus you have to do this exercise. So this is distribution, a joint distribution for all Ci's, right? And what I want to do is to find distribution of one component. So how to think about this problem? This is an equation that determines a sphere in n-dimensional space, right? And what I want to do is to integrate over all coordinates except one. So, and you remember that at large dimensions it's possible to use saddle point, gamma functions. This is beautiful stuff, so I'll skip it all and just write the answer. For orthogonal ensemble, when Ci's are real, it's 1 over square root eta minus eta over 2. And for unitary ensemble, it's even simpler, just eta minus eta. And this here. And so all these statements about eigenvectors are known as Porter-Thomas statistics, and it's old paper of Porter and Thomas, 1956. I gave a reference in notes. The energy level repulsion was basically conjectured by Wigner, and that was in connection actually with nuclear physics. So if one takes a heavy nucleus, and I think that one of the kind of guinea pigs, or Drosophila flies rather, is thorium, and scatter relatively high energy neutrons. So at low energies, one sees shell structure, but at high energies, the spectrum of resonances of scattering of neutrons of a heavy nucleus that has many neutrons looks complicated. And Wigner had an assumption that maybe it can be described statistically. And this matrix 2 by 2 that you had as a home exercise is, this exercise is called Wigner surmise. So my English is not good enough, but surmise is something like assumption, I guess. So that basically was a kind of a simple explanation of the structure of the peaks, the distances between the peaks that never come close to each other. But there is another thing, that peaks are different. One peak is different from another peak, and apparently there is not much relation. And that was explained by, or I don't know, conjectured by Porter and Thomas, that maybe the description of the amplitudes of these peaks may be related to the distribution function of the wave functions, which can be related to resonant widths or resonant amplitudes. So I'll get back to that in a less vague way in connection to solid state physics or quantum dots a bit later.
Question?
Yes.
Just to clarify the notation, should eta have a subscript I? I mean, is that amplitude with the eigenvector on site I squared?
So they are, I can put here I, but the point is that it's independent of, I can look at any component of the vector and they all distribute.
M is a scalar, it's the dimension of the vector.
Pardon?
M is a scalar.
Yes, M is a scalar. It's a big scalar, yeah. Right. So actually, that's just to prompt So this is kind of abstract in some n-dimensional space for matrices. So what is the relation to real space?
Good question.
Yes.
Are there finite-sized corrections to this random matrix theory for m not a million?
Yeah, it's also a good question. So one must two things. One is that okay, one can consider finite-sized metrics, okay, and then develop some understanding of what happens. For example, if you look at levels that are far away from each other by amount larger than m delta e, one can do that, and it's a legit thing. And there is a proper part of RMT theory that discusses these kind of things. Okay. Now, another thing is that is it relevant for physics? And not necessarily, because basically, physically, if we go to energies larger than Taoist energy, well, things change in the sense that we don't have any more diffusion motion. So there is no guarantee that if you find something from RMT, from finite size corrections somewhere, at, say, energies larger than delta than ET, it will correspond to any physical situation. So there are two separate things. And there are cases when it's interesting, and there are cases when it's less interesting. Is an example where I think, well, I'm not sure that I remember it, but I think that in the question about deep level, if you have a superconductor, it's one of the classes that actually Chilke will discuss. So if you have a superconductor with broken time reversal, there are deep levels inside the gap, and probably some properties of these deep levels are related to the kind of corrections you're asking about. There are papers about, I think related to this question, you will look for Lamacraft and Simons. And probably one of their papers is related to this question. I'm not sure, but possibly. Okay.
Question?
Yes.
Could you please explain again why m has to be much greater than e in the Thouless energy divided by the level spacing?
Right. So it's related to the question. So basically, let me maybe try to give a pictorial answer. So if you have matrix m by m, the level spacing for this matrix is delta e. Okay. Now clearly, if I go to very high energies or very low energies, perhaps I will not find any eigenvalue. And indeed, the density of levels, let's call it rho temporarily, is a function of energy. For random matrix looks something like that. It's called semicircle law. Okay. And from the physics point of view, I'm sorry to say it, but all of this is crap. The only thing that we need is in this part where rho is almost independent of energy. Okay, so that's why I want this to be large, so that I'm sure that as long as I'm inside energy interval of order of Thouless energy or less, I can forget about it. And that's basically the idea. Okay. And the finite size corrections, one of the questions that one can ask in terms of finite corrections is what happens here. And it's not abrupt, there are some tail and so on.
Is rho density of state C?
Right, yeah, density of levels.
Why is it circle, semicircle?
Well, I don't want to, I mean, the only thing I'm saying here is that it should die out when I go to high energies, okay? So why it's semicircle is possible to show, but I will not do it.
So it's possible to show within random?
It isn't empty yet,
Okay.
yeah. Again, if you want to look at mass of this stuff, I think that the kind of the, I'm not sure that the best reference, but very highly cited reference is Mechner random matrix theory. It's somewhere in the beginning you will already do. Yeah.
Sorry, just in terms of the properties of the matrix elements, can you remind us the difference between the orthogonal and unitary ensemble?
The difference.
Yeah.
Right. So in orthogonal matrix elements are real.
Okay.
In unitary matrix is still Hermitian, so Hij equals Hij star, but they're complex.
I see. And this has to do with time reversal.
Yes. Yeah.
Okay. Thank
And yeah, and then I didn't want to speak about this now, but it's unitary and orthogonal, and we're talking about real complex numbers. But actually, for physical system, or for electrons, there's also spin. So proper generalization is called symplectic ensemble. So the symplectic ensemble is time reversal ensemble that accounts for spin. So if you take a piece, it's a topical subject. So if you take a piece of topological insulator, it has strong spin-orbit interaction, and cut out a piece of it, those pieces will be described not by GE or GOE, it will be GSE, the symplectic ensemble. So each level will be doubly degenerate, according to Kramers, but the level repulsion will be different from what you had in exercise at home. Yeah.
So in a localized system, eigenvalue statistics are Poisson instead of
Yeah.
Gaussian.
Right. Yeah.
Is it known what random matrix ensemble describes a localized system?
Okay. So RMT should. Okay. So it's a programmatic question. Very good. So RMT should not describe localized system. Okay. If RMT, if you are claiming that RMT describes localized system, something is wrong with the localized system or with you. Because in localized system, distant sites which may have the same energy will produce states that don't repel each other. Right. So statistics will be dramatically different. And one last question: whether you can describe crossover between localized and delocalized states by RMT, and I think the answer is no, although there are papers about it. So does that make the answer? I mean, the physical question and deep question is that if you have, just a second, so if you take a material at Anderson transition, okay, and cut a piece of it, what will be the level statistics? It's a beautiful question, and I'm not sure that the answer is fully established, but there is lots of numerical work and some analytical work. And again, you can look for numerical work. It's Kramer, Shklovsky, in different combinations, not together. No, I mean there's not any kind of question. It's just it's okay. And there were analytical papers. I think Lerner, definitely Lerner and Altschuler, early 90s. But perhaps I didn't follow it. There are way more papers.
For a highly disordered Hamiltonian, even if it's not self-averaging because it's localized,
Yeah.
can one understand why there should not be a random matrix description? Because you might think I could write down.
Yeah, I mean, look, perhaps one can understand it in very sophisticated terms. I mean, I'm not even a practitioner. I'm just using it in a very trivial, simple way. For me, I mean, transition means G order of 1. G order of 1 means ET order of delta E. So it's matrix 1 by 1, right? So it doesn't make sense. That's all the matter of it. Random matrix description may make sense if I have large M and I can pick this part, okay? And if G is order of 1, then simply there is no this thing, and I cannot pick a part that has constant distance. Okay, so getting back to real space, this statement has a counterpart that the wave functions in real space eigenfunctions of different levels in real space are not correlated, so it's delta, alpha, beta. And this is true for GE or GOE, but in addition for GOE, there is a correlation between well, there, okay, I will write it. So this is general for any ensemble G or G, and then for orthogonal you can also take out the star, it will be the same thing. So so now the question is, yeah, maybe one more thing. Yeah, this is good. So now, if I set alpha equals beta, then I'm interested basically in the correlation function for the same level, but at different points. And the counterpart of this kind of statement would be that this is 0 for distant points. So one may think of real space cutting in cells of the size larger than, say, min3 plus. Okay, and a simple statement would be that the values of eigenfunction at different bins are independent of each other. It's kind of a crude statement that corresponds to the fact that in random matrix you can rotate the wave vector in m-dimensional space. But I want more. I want also to know how this correlation function behaves at distances much smaller than Fermi wavelengths. And for that, I can use the following calculation. So I'll write down the imaginary part of green function. And in terms of eigenfunctions, it's sum over beta phi beta of R1 phi beta of R2 star delta R1 minus R2. And then I can integrate this relation over a small interval around level alpha. I integrate and average over disorder. And then I can switch the order if I need. So basically, the left-hand side here can be evaluated quite straightforwardly because I have a machinery to evaluate average values of green functions. And the right-hand side will give me just this quantity. Yes?
So that function you need energies. No?
Oh, I'm sorry. That was really bad. Epsilon minus epsilon beta. Thanks. Right, so doing that, one gets phi alpha of R1, phi beta of R2 equals delta alpha beta times 1 over volume. I'll put here sub d for dimension d f some function of kfr, kf R1 minus R2. So basically this f is what Andreev had for a single particle green function. I can write it in a compact form as average of e to I kr over the Fermi sphere. And if you're interested in asymptotes, so for large distances, for KFR larger than 1, in 3D it's 1 over r times e to I KFR, maybe with minus sign, and in 2D it's 1 over square root. Basically it's a Bessel function, and asymptote is 1 over r KFR. E to minus I KFR, plus KFR. So So indeed, this function does decay at large distances and oscillating. And this expression works for any distances, including, and most importantly, for distances less than mean-free path. Okay. So there are some remarks that other ways to obtain these relations, and you can look in the notes for that. So now another average that we will use in really few minutes is average of 4 wave functions. And within RMT, basically, these averages are also easy to evaluate. Well, I would not within RMT, better say in the zeroth order in 1 over conductance. It's easy to evaluate, basically using the same kind of technique. So I'll write product of 4 wave functions in a minute, express them in terms of grid functions, and then do average and integration, then take delta over to small enough so that only one level is singled out, and write the answer.
The piecewise function has the same condition for both.
Say again?
If both are KFR greater than 1, much greater than 1.
Right, and it's 3D.
Okay, yes.
It's 3D and it's 2D.
Okay.
Okay.
Excuse me?
Yeah.
So, did you say you're also taking disorder averaging here?
Oh, yeah, absolutely. So this brackets.
So the
Is disorder.
value of average is independent of strength of disorder.
Right, yeah, that's also an important point. So as long as I look at distances less than mean-free path, for direct also here, so R is much less than L. So in principle, mean-free path depends on disorder. Okay, that's also a good point. So although I'm thinking of disordered, well, as I spoke yesterday, Curie cutter applied to aluminum foil, but in case of semiconductors, actually, use situations that pretty clean quantum dots. So basically, electrons bounces off walls without any scattering inside, but walls are not necessarily forming a circle. So if it's some stadium that leads to chaotic motion, then all this holds, and basically this little L is replaced by capital L for the size of the system. Okay. So one more lengthy relation that we will use. So phi alpha of R1, phi beta R2, phi gamma R3, phi delta R4, star star, and greatness delta alpha delta delta beta gamma F14 F23 plus delta alpha gamma delta beta delta F13 F24. And the shorthand here is that Fij is F of Kf Ri minus Rj. And this is GE. In a octagonal ensemble, there is additional term delta alpha beta delta gamma delta because I can also pair this together. Okay, so a few final remarks. The first remark.
Sorry,
Yeah, go ahead.
do you not need this B sub B factor that you have in the 2.4 already?
Say again?
Why do you not have a B underscore D?
1 over V sub D. Yeah, maybe I need it. Yeah, perhaps I need it. You know what? I think you're right. I think I need it, but you know, you can check. I mean, so basically, this is even in notations that I think that are identical. Is I have a review article, and it's quoted in these notes. It's Alina Brouwer and me, and it's somewhere in the beginning. It's all coefficients checked. So. And also, I think that there we have also for GOE, but I'm not sure. Was some time ago. So now, so if we know eigenvalues, the Hamiltonian in second quantization of free fermions can be written as epsilon alpha, d alpha dagger d alpha, where operator as d was introduced last time. Epsilon alpha is the RMT spectrum. The second remark that I already said that if it's chaotic rather than disordered dot, everything holds, and basically the mid-free pass becomes the order of the size of the system. And final remark about the crossovers between ensembles. So once again, there is a axiomatic way to look at the crossover between ensemble. Basically, it introducing two matrices with different symmetries and some linear combination of the matrices. So it's a formal way to look at the crossover set between a orthogonal and unitary ensemble. And we can find in RMT literature. But then there is a question physically how the crossover, which parameter you have to tweak in order to make the crossover, and by how much you tweak the parameter to get the crossover. And that, at the intuitive level, goes back direct to the question about diffusion equivalent that we discussed. So if you remember, when we looked at level repulsion at distances larger than delta epsilon, we had 1 over omega squared times 1 over beta, where beta was this 1 over half depending on ensemble. And we understood that basically these two limits correspond to the Couperon contribution present or absent in the level repulsion. And we also know by how much you have to tune the magnetic field in order to suppress Couperon at certain energy scale. You remember that we had the correlation flux phi c of order of phi naught over square root g, and that was enough to suppress Couperon at energies of order level spacing. So basically the physical picture is very simple. If you want to go from orthogonal to unitary ensemble and see how level repulsion changes at the scale of level spacing, it's enough to thread this flux. You crank up the flux, and more and more distant levels start to feel the change of the ensemble. When the flux approaches phi naught, you made a crossover from orthogonal to unitary in the energy interval of order of tau energy. And that's something actually that experimentally is interesting and observed, for example, in measuring of persistent currents. And that's relatively recent measurements that finally got persistent currents right. Indeed, this basically current experiments are always in unitary ensemble, but the question is how far unitary ensemble, and these considerations do play importance in this kind of experiments. So that's all about free fermions, and now I'm going to the next part, turning on interactions. So we finished with the item 1 in the plan, so from 1.1 to 1.5, and now we go to 2.1. And it's the description of interactions by a universal Hamiltonian. So I will think of density-density interactions. Okay, and density-density means that the Hamiltonian must have two psi diagrams and two psi, right? So the density is psi diagram psi times psi diagram psi. But I'll normal order them. So H alpha, beta, gamma, delta, d alpha, sigma 1 dagger, d beta, sigma 2 dagger, d gamma, sigma 2, d delta, sigma 1. And again, I emphasize that I look at mass density, therefore, these speed indices are equal pairwise.
What are the sigma labels?
Speeds. Right, yeah. So maybe, you know what, one more remark that I wanted to make about RNT. So among crossovers, okay, so unitary to orthogonal actually can be described in non-gory details. It turned out that an interesting crossover to discuss, so I'm switching back a little bit for a sec, is crossover between symplectic and unitary ensemble. And that corresponds to the following question. So suppose you have a metal gray, okay? And without magnetic field, all levels are Kramers degenerate. So each level is doubly degenerate. And actually can measure the energy levels by some tunneling experiment. Then you apply magnetic field and the levels split. Zeeman splitting, you know it, right? It's not a big deal. But the thing is that if you have spin-orbit interaction, maybe you know from kind of basic solid state that spin-orbit interaction does affect G factor. And the corollary of that for a finite system is that the level splittings become random. So the G factor is unique for each level. Moreover, this G factor is a tensor. Depending on the direction of the field, splitting is different. So you have random G factor, and there are statistics of these G factors. And the statistics is a question about the crossover between the symplectic ensemble and unitary ensemble. So you apply magnetic field, you start to deviate from symplectic, okay? It means that you introduce some small splittings between the levels. And the statistics of the splittings is actually statistics that is described by this crossover ensemble. And I don't think, if you want your muscles trained, you may try to describe this whole crossover. I don't think it's done, actually. So that's a good mathematical exercise. You definitely will be able to publish it. Okay, so back to interactions. So the matrix element, just by definition, is phi of R1, phi beta R2, V R1 minus R2, phi gamma R2, phi delta R1, and again, no spin orbit, so these wave functions are just orbital wave functions. So these wave functions are random, and our goal will be to see that actually the interaction Hamiltonian can be written in the following way. There is a part that is non-random, okay, and large, and there are corrections, intermediate correction in 1 over G. So once again, this whole theory is based on small parameter, which is 1 over conductance, meaning that we are looking at good metals. Okay, so we look at good conductor, just a finite piece of it. And this part, which is a correction, it scales at some power as 1 over G. It has lots of matrix elements, but these matrix elements are small as 1 over G to some power. And this part may be random. It contains random parts. Now, yes.
Why is there this corrective part? Usually you have some Hamiltonian. You can diagonalize it, and phi alpha betas are all the eigenstate waveforms.
So phi alpha betas are single particle
Right.
wave functions, right? And upon the integration of free Fermat Hamiltonian, I'm getting that. Okay. So now, when I put in interactions, okay, there is additional part of Hamiltonian that looks like that.
Right.
Okay. And my question is, what can you tell about the physics elements? Okay.
So E alpha are the energies in the clean system.
E alpha are energies in a disordered system,
Okay.
but without interactions. Okay, so I have first, like in thermodynamics, we start with free fermions and then put in interactions, and find out that interactions don't change things much, right?
So, but I don't understand. Oh, I see. It's the same H int that you're breaking up into 2 parts.
See it?
So
It's H int. It's just
the full thing.
this thing.
I see.
It's only interaction. Okay, so yeah, maybe I should. So the full Hamiltonian H is HF, which is bilinear indeed.
Right.
Okay, plus H int, which is coordinate. Okay, and then what I'm trying to say is that to tell that there is a certain hierarchy in the matrix elements. Okay, there are some that are large and don't fluctuate, and there are some that are small and fluctuate. Yeah.
So from going from free to interacting picture, interacting system, we are dealing with that. There we're dealing with single particle problem, and there we're dealing with many body problem. Is that correct?
So I'll follow Clinton. What do you mean by dealing?
Just the single particle, it doesn't interact with anything because it's a single particle, and for interaction we need at least 2 particles to.
Well, it's a Hamiltonian. So in the Hamiltonian, there is interaction between particle and particle. That's true. Then you ask questions that you could ask also for free Hamiltonian. For example, I can ask a question. Somebody asked last time about density of states. Okay, I can, and it's imaginary part of single particle wave function G, R, epsilon, RR. Okay, the dependence of energy will drastically change. Okay, it will start to depend whether energy is high or low compared to Fermi energy, Fermi level. Sorry. So I'm asking the same question that I asked for this Hamiltonian, and the answer will be different. Or I ask questions that didn't exist before. And I think I'm eager to give an example at the end of today, of this lecture, is question about relaxation. So I'm going to ask a question whether electron that has initially energy epsilon will decay or not. Here, no way, right? But with this Hamiltonian, maybe. Okay?
So then that part is not in the made by localized space because you're expanding in 1/G.
No, that's just more complicated. So, in many ways, a localized state.
Because there you can't apply.
I'll get to the foot of that mountain towards the end of the lecture and defer the rest to Hughes. Okay, but I will touch upon that, I promise. So I hope not touch. So it's the number 4 in the list is finished. I mean, at the very end of it, it's this question, the introduction of this question, and you can actually look at the notes and see that. So I'll get to that, I hope. Yeah.
So we feel the small parameters 1/G, there are also like some parameter which controls like interactions which are not density like.
No, interaction is density, but
I mean there are
exchange is also density. Well, exchange comes from density, right?
but I mean when you
There is microscopic density interaction, which was rho times rho. Then you write it down in matrix elements. You can single out the exchange part and Hartree part. We will do it in a minute. But it's not separation between H0 and H1 over G. Okay? Yeah?
I guess you said you have crossovers between the different ensembles. You never have a sharp transition for the free fermions.
Crossover between ensembles is a question about free fermions, right? So
Yeah,
it's
but you would never have a sharp transition in the statistics of energy levels.
Okay, so once again, this question requires a bit of clarification. So we were discussing single particle states, right? So if I have no interactions, then spectrum of many body system can easily encode it, this in terms of single particle states. And I discussed the statistics of single particle states. If there are interactions, then, as was mentioned, I might think of many body levels, but there will be no such a simple encoding in terms of single particle levels. So if I'm at low energies, and I will qualify it towards the end of the lecture, if I'm at low energies, then roughly speaking, interactions are not important for these crossovers, and you can still think of crossover in terms of properties of epsilon alpha. And I don't know how to ask the question correctly for higher energies, where we're talking about many body states rather than single particle states. So that's a partial answer to your question. Okay. All right. So let's maybe get back to that. So the first thing that I want to say is that the general form of this part actually can be established without calculation, just from looking what are the invariants of the RMT, right? So if this thing is not random, then it should consist of invariance of the distribution of the random matrices, and there are invariants of this distribution. Let me erase it. And those are the total number of particles. Okay, so total number of particles does commute with the Hamiltonian, obviously, right? So with this one and with that one. So n hat, which is sum over alpha sigma d dagger d, is invariant. Another operator which is invariant is total spin. And again, there is no spin-orbit interaction, so that's why this is also a conserving quantity. Alpha sigma 2. And finally, there is one more invariant that comes. Well, actually, I'll just refer to Tucker's lectures. So this invariant is D up-down operator, and it also should be invariant with respect to RMT. So that comes from this, that comes from SO2 invariance, that comes from particle conservation. Yeah.
When you say there is, do you also assume that there is no fluctuation of these quantities? Or averages?
Okay. So what I'm telling you is that there must be some. This is an operator. Okay? So now the question is, if I want to express this operator in terms of these operators, okay, what I'm telling that I can express in these terms this part, not fluctuating.
Oh, invariance is a language in that description, and it doesn't mean that number of particles is fixed all the time in the answer.
No, I might change, but I'm saying that number of particles does commute with the Hamiltonian. Okay. So this part can be expressed in these terms, and this part not necessarily. Okay, again, small part.
Can you explain once more what is the meaning of this T?
Okay, so as you see, it does concern number of particles, and that's something that can be useful for BCS instability. So this Hamiltonian is 4-fermion Hamiltonian. So if you look at BCS, I can mimic this guy, the usual BCS thing: d dagger up, d dagger down, d down, d up. Okay. then corresponds to the possibility of adding this operator here.
Is it U1 gauging there?
So now another thing that